A sample of methane gas was collected by displacement of water in a gas collection flask. The total pressure in the collection flask was measured to be 758.2 torr at a temperature of 25.0 degrees Celsius. And the measured volume of the gas in the flask was 526.0 milliliters. How many grams of methane was in the flask? And we're told a very important piece of information. At 25 degrees Celsius, the vapor pressure of water is 23.8 torr. That's important to know because since the gas methane was collected by displacement of water, we have two gases in the flask. We have gases from the methane molecule and we have water gas molecules as well. So again, this is a partial pressure problem, but in reverse from problem number 8. Our total pressure then in this particular problem is going to be equal to the pressure of the methane, which is what we're interested in, plus the pressure of the H2O. But this is very simple now because we're given the vapor pressure of water 25 degrees Celsius. They tell us that number right here, 23.8 torr. And we also know the total pressure. That number was given to us in the problem, 758.2 torr. So our first step then is to just simply calculate the pressure of methane in this flask. And once we have that, we can use the ideal gas law equation to calculate the number of moles and therefore the number of grams. So let's do our subtraction then. Our pressure of methane is going to be equal to the total pressure minus partial pressure of water. Our total pressure was given in the problem to be 758.2 torr. And we're going to subtract from that to 23.8 torr. We're told the vapor pressure of water at 25 degrees Celsius is. When we subtract these two, we get a vapor pressure of, we get a pressure of 734.4 torr. And that's going to be the pressure of our methane, CH4. So now that we have that, we can go ahead and use the ideal gas law equation to solve for moles of methane. PV equals nRT. N is our unknown. This is what we're going to solve for, moles of methane. And now we are going to do some algebra. N, therefore, is going to be equal to PV over RT. And now we're going to substitute numbers in. Now, our pressure is given in torr. We're going to have to convert that to atmospheres. So let's do that. Let's erase this. We know what that is, and I need a little space up here. So let's take our pressure of methane, 734.4 torr. Our conversion factor, 1 atmosphere over 760 torr, exact number. And we do the math, we get a value of 0.9663 atmospheres. Okay, so now we can substitute in, and that's our first variable, 0.9663 atmospheres. Volume is next. That's given in the problem. We're told that the volume was 526.0 milliliters. We need liters, divide by 1,000. So we get 0.5260 liters. Downstairs, our gas constant always would be given 0.0821 liter atmospheres per Kelvin mole. And lastly, our temperature was 25 degrees Celsius. So we're going to add 273.15 to that. So we're going to end up with 293.15 kelvins. So now we're good to go. For some reason I keep losing stuff here on this tablet. Let's check our units here. Our liter is going to cancel. I've got upstairs, upstairs, and upstairs, downstairs. Same is true for atmospheres, so they're gone. Kelvin is upstairs, downstairs, and downstairs, downstairs, so they're gone. Moles is downstairs, downstairs, which means when I do the math, I'm going to get moles upstairs. So doing the math, N is going to be equal to 0.0208 moles. And we do have three significant figures on that from our gas constant R. And now to calculate the mass, we're simply going to look up the molar mass for methane, which is 16.04. We used that in the previous problem. So our starting point is the number of moles, 0.0208 moles of methane times 16.04 grams per mole. Moles cancel, left with grams of methane. Do the math, I get 0.333 grams of methane in this flask.